So our first lab this semester is an electric field mapping experiment. We'll show you the equipment in a bit, but I need to talk a little bit about the theory. First of all, electric field. Yes, it's a vector. So E is the electric field, and we will talk more about this. And we'll be getting into some things that you're not going to get to in class for a couple of weeks, but I'll have to talk about them anyways because you'll need the mathematics to do this lab. So E is the electric field. First of all, what is an electric field? Okay. We've already dealt with fields, and if you didn't read those parts of the chapter, I think it was 13, on gravitation that we didn't have assigned to you, then you won't know this. But G, back in the good old days, last semester, G, which of course is a vector which points down towards the center of the Earth, is the acceleration due to gravity. Not gravity, it's acceleration due to gravity. G is also the gravitational field vector. Well, this requires a story, and my distortion of history is as follows. In England, in the late 18th century, 1780, 90, whatever, and early 1800s, England was undergoing the Industrial Revolution, first of any country in the world. And they were very practical. They were inventing steam engines to empty their coal mines so they could mine coal better and faster and so forth, and inventing steam engines to drive people up and down on rails for trains and all kinds of wonderful stuff going on in around 1800, give or take 20 years or so, or maybe 40 years. So they're very practical people, whereas on the other side of the English Channel, we had the French, and they were very philosophical people. Okay, so we had these practical, philosophical attitudes across the English Channel. And the question really is, and we should have asked this question last semester, if you have something on Earth and it's sitting on Earth, of course there's a force on it. It's called the force of gravity, and it's equal to m times g, where g is the gravitational field vector now, or the acceleration due to gravity, whichever way you want to look at it. And so this is a vector, and g points down towards the center of the Earth. So that's what we talked about last semester. We could draw force diagrams and do calculations, and this is the weight, and that's the mass, and we know all that stuff. That's the acceleration due to gravity, and so on. But what if you pick this object off the ground and you let it go? It would still have a weight. It would still be near the surface of the Earth. It would still have a weight of m times g, 9.8 meters per second squared. But it's going to fall. So there's a force on it. There's a force on it here. It's just sitting there. It's a static force. There's a force on it here. If you let it go, it's going to fall. And you can calculate the acceleration. This is way back to chapter 2 and 3 in last semester, where we have the equations of motion. You can find out all about it. Its velocity, its time, its acceleration, its position, all that stuff. But the point is, there's nothing in between this mass and the Earth. So what is producing that force? I mean, I thought forces were pushes and pulls, and you had to be in contact to have something be pushed or pulled. But gravity is pulling on this object, and there's nothing actually pulling on it. So the French said, yeah, c'est la vie. That's the way it is. They were philosophical about it. Again, a rather bad distortion of history. And the English said, no, there's got to be something doing that. Let's be practical about this. And so the English, again, a slight distortion of history, the English invented the electric field. Now there's something pushing on it. So if you have, similar to this, if you have an electric force and you have an electric charge, which for some reason we call Q, and that's in an electric field, you have an electric force on it, very much like what we learned last semester. Okay, so a charge in an electric field experiences an electric force. A mass in a gravitational field experiences a gravitational force. And we didn't need this field business. We can get along without it, but in fact, this is a way to interpret what G is. It's a way to talk about how there can be a force when there's no contact. This is called, cleverly, force at a distance. Okay, so a force at a distance is kind of a puzzle. How does it do that? Again, the English said, well, there's got to be something there. We're going to make it be called the electric field. If you have a charge in an electric field, it automatically experiences a force on it, instantly. So we have these invented electric fields. They're very handy. It's called a handy fiction, if you want to say it that way, a convenient fiction. There's not really a field there, but it seems like a field. I mean, there's something there now, which makes the English happy. When you put a charge in a field, it experiences a force right away, no problem. First of all, you know that, talking about astronomy, if you look at the light from Alpha Centauri, which is the closest star to us, it's about 4 light years away, which simply means it takes 4 years for light to get here. Light travels at 186,000 miles a second, or 300 million meters per second, whichever. I prefer the latter, but whichever you're used to. And so it's the fastest thing we know of that can travel at that speed. That nothing with any mass can travel any faster than that, or cannot even travel quite that fast. But that's getting into relativity. So it takes 4 years for light to get from Alpha Centauri to here, which means that if Alpha Centauri exploded for some reason, we wouldn't know about it till 4 years from now, because it takes 4 years to find that out. So there's kind of a time factor there. The universe is roughly 14, 15 billion years old, which means the light coming from the edge of the universe would take 14 or 15 billion years to get here. And we can see, I'm not up on the latest numbers, but we can see, so to speak, 13 billion years or better back into time, we can see light that's coming from something that was there 13 billion years ago, or more than 13 billion years ago. And so that's with a really good telescope in outer space, like the Hubble telescope. So that's what we're faced with, pushes and pulls, mechanical forces, or action. Newton's word for force was action, by the way. So action at a distance means force at a distance, which is what we've just been talking about, through nothing. And as I say, the English didn't like that, so they invented this electric field. So if you have a charge, if you put a charge there in space or on a board, that means that charge sets up an electric field everywhere around it. And that's kind of what we're looking at today in this lab. So if this is a plus charge, we say the electric field lines come out of plus charges and they go into minus charges. So we have electric field lines that are radiating out in all directions. So here's some electric field lines. Those are electric field lines. So this charge, you might say that charge number 1 produces an electric field all around it. Everything that's charged in the universe produces an electric field all around it. The bigger the charge, the bigger the field. It's just a linear relationship. So we'll call this Q1. Now, if I have a charge over here, Q2, then this charge is in this electric field. Here's one of the electric field lines coming over towards Q1, or Q2, I should say. So this is an electric field line from charge 1 over there coming towards charge 2. And if they're both plus charges, as you'll find out shortly, plus charges repel each other. Opposite sign charges attract each other, which adds another little complication to our force discussions. You have to know which is which. Are they attractive or are they repulsive? So, the way we look at this, the way, at least I'm going to say it my way, this charge, the initial charge all by itself, sets up an electric field all around it. Everywhere in the universe, everywhere in space. I mean, you get far enough away from it, it's not very significant, but close to it, it sets up a field which gets bigger. And you can see, by the way, that's one important thing coming out of today's lab. You can see the field is stronger here. You can draw a picture of it because the field lines are closer together. And the field is weaker here. It gets weaker fast. In fact, it gets weaker as 1 over r squared, as you can imagine. It gets weaker as 1 over r squared as you go out here. The field lines are this far apart over here, so the field is really weak. And it dies out as 1 over the square of the distance between these two charges. And we'll write that down in a minute. That's called Coulomb's law. That's the first thing you're going to talk about, or have talked about this semester. Okay, so Coulomb, let me say that now. Coulomb's law is equal to some constant to make it equal times Q1 times Q2 over r squared, where r is a distance between these two charges. And it's a vector, and it's a vector in the radial direction, which means it's a vector along the line joining the two charges. This is the direction r. If the charges were here, that would be the direction r. Okay, so this is Coulomb's law, the first thing you'll talk about electrostatically this semester. And K is Coulomb's force constant. And in fact, K is 9 times 10 to the 9th. And I won't put the units down necessarily right now, but the point is 10 to the 9th, that's a billion. That's a big, strong force constant. These are big, strong forces. That other force constant for gravity, by the way, you may remember last semester, this was the force of gravity. Of course, it's F equals mg, but this actually is g. That is, it takes two masses to have a force between two masses, and that's the force between two masses. And so g m over r squared, where g is a number, it's 6.67 times 10 to the minus 24. It's teeny tiny. It's 32 orders of magnitude smaller than that. So electric forces are really strong. You have to have really big masses to have a really big force gravitationally. The Earth's mass is 6 times 10 to the 24th kilograms. That's a really big mass. And so even if you have a small mass near the Earth, it has a pretty big force on it. That's called the force of gravity. Okay. So there's this charge sets up a field. The way I like to describe this is that this charge here, just forget about this charge for a minute, this charge here sets up some kind of a, quote, disturbance in space all around it instantly. And when you put this charge in it, it's affected by that disturbance. If the charge weren't there and you put this charge here, it wouldn't have a force on it. But if you put this charge here and there is a force there, then there's this force right here between those two charges, Coulomb's force, repelling each other if they're both plus charges. So that's what I mean by this charge by itself, one single charge, sets up a field which is everywhere in the universe instantly. And if you put another charge anywhere in the universe, that charge instantly feels a force caused by that other charge over there. So if you divide Coulomb's law by the charge that isn't there, which I'm calling Q2, then what we have left is the electric field. So this is the electric field. That's the strength of the electric field for a single isolated point charge. And again, it depends on 1 over r squared. That's just the spherical geometry here. So if you go twice as far away, the field is 1/4 as big. If you go 3 times farther away, the field is 1/9 as big, as strong, I should say. So this is the electric field. That's a form of the electric field of a single isolated point charge. Just that. That's what it looks like. We can draw pictures of it, because if I know I put a charge over here, it's going to want to go that way if it's a plus charge. If I put a charge up here, it's going to go that way if it's a plus charge, and if it's a minus charge, it's going to go that way. It's all very simple. You can draw pictures of it. Like we drew force diagrams last semester, we can draw field diagrams and see what the field looks like due to a charge. Of course, that's the simplest field, or maybe a bunch of charges. Well, that's in another chapter. You'll get to that. So, a single isolated charge sets up an electric field everywhere in the universe, all around it. It's stronger when you get closer, but it's there. And when you put another charge anywhere in the universe, it experiences a force, large or small, caused by this charge, and it's existence of this charge here. So that's the way I look at electric fields, which are forces, actions at a distance. Whether they're gravitational forces, actions at a distance, 2 masses attracting or repelling each, they only attract each other. But here we can have attracting or repelling forces, because we can't have plus and minus masses. We have plus masses. Either you have a mass or you don't. And so there's no such thing as a minus mass. Even antimatter, if you know anything about it, has a plus mass, even though it's anti. So it has an anti-charge, that's all.